Welcome. This is going to be the second part of really process, probably the fourth part of moderation mediation. And so in this particular class, Class 8, we're going to talk about process moderation and mediated moderation or moderated mediation. I mean, you can view it a lot of different ways. So that's what we're going to be talking about. So again, you probably remember from last class our definition of moderation. Moderation is the combined effect of two variables on another. It's known conceptually as moderation, and in statistical terms as an interaction effect. And then here was our definition from Wiki. Again, I'm not going to read through this all again. I've read through it before. You can always, if you want to read through it again, you can stop the video and read through it. And if you remember, we went through a number of examples, but this would be the classic example of moderation. So again, the classic example of moderation would be general mental ability causes or leads to our GPA in college or high school, but that is moderated by demographic variables. So our general mental ability is not as valid for all different groups. Now, of course, that's a testable hypothesis. It might or might not be true, but that's what we're hypothesizing. Our moderator is then a demographic variable of some kind. Of course, we can have more complicated models. Here we have two types of moderation, and we have mediation. So here we have general mental ability leading to job knowledge, leading to job performance. But both of these paths are moderated by demographic variables. So the path from general mental ability to job knowledge is moderated by demographic variables. The path from job knowledge to job performance is moderated by demographic variables. Okay, now we're going to go back and we're going to repeat our previous moderation analysis. So we've seen Field do a moderation analysis. Now we're going to repeat our previous moderation analysis. I'm coming to you to interrupt this TV show to just make a correction. So just so you have it correct as we go through these slides, I want you to know or remember that despite what I say, death pop is deaths per million. It's not per thousands or hundred thousands. It's actually deaths per million. So again, the error, the problem came about because the world site uses deaths per million for each state. On the other hand, most other people use deaths per 100,000, and also for most of the other variables, they used 100,000s or things per 100,000s. So I actually changed in the database the variable or created a new variable that was deaths per 100,000. But then a lot of times I still went back and used the death per million variable by my error. So all it does is put anything off by a factor of 10, really. It doesn't affect the interpretation of any of the analyses, but it does put things off by a factor of 10, and I apologize for that. But instead of changing all the slides, I'm just letting you know that whenever it says death pop, that's deaths per million, not per thousands or hundred thousands. And I thank you for your understanding with this issue. Our previous moderation analysis was with predicting COVID deaths in the population for each state, and the dependent variable, or the Y, was actually deaths per 100,000. We also had density, or density of the population per square mile, and average temperature in the state. And again, our sample size is 50. We have 50 states. And now this time, instead of running SPSS, we're running process. And you can go back and you can compare now these results from running process to the results from when we ran SPSS in the earlier class, if you would like. So we run it, and here's what the output's going to look like. I'm sorry if this is a little hard to see. This time I wanted to give it all to you. I didn't want to cut it off, but it does, I admit, make it a little harder to see. You might have to squint a little bit. So we can see our model summary. The overall R is 0.61. The R squared is 0.38. That means our model is explaining 38% of the variance in COVID deaths. Our mean square error, our F, 9.31. Degrees of freedom, associated degrees of freedom. You know, we have 3 degrees of freedom because we have 4 parameters. And then our p-value, 0.00. Then we have our model. You can see our constant, which is really just an interaction. Our density, which again, density here is our independent variable. And density has a coefficient of 0.78. It is significant at 0.00. And here's our bootstrap confidence intervals. We then have temperature. Temperature is also is not significant. So the P there is 0.38. So temperature itself does not affect COVID deaths. But the interaction, which the interaction is density times temperature, the interaction is significant. So as we saw before, there is a significant interaction. And here's the bootstrap confidence intervals. And here's the B coefficient for the interaction. Here's a test of the highest order unconditional interaction. In this case, there's only one interaction, so it's going to be the same thing as what we saw up here. And then here's our conditional effects of the focal predictor at values of the moderator. So again, this is similar. I should have said this on the previous slide. In ANOVA, this is similar to simple main effects. You know, so probably in ANOVA, you talk about simple main effects. This would be similar to simple main effects. Although, of course, we have continuous variables. So in this case, we have continuous variables, not categorical variables. But this would be similar to simple main effects. So here we have our conditional effects. Again, temperature 1 standard deviation below the mean, temperature 1 standard deviation above the mean. And it's just showing you the regressions or the effects at those points. Again, I think it's easiest once you actually go ahead and plot this. It's easiest to know what this means once you go ahead and plot this. So we're going to go ahead and plot it. Well, again, as did Field, a process will actually give us this syntax that we can just load right into SPSS. So it gives us the syntax to load right into SPSS. These are the density values, the temperature values, and the predicted values for deaths per 100,000. Note, I could, if I wanted to, just go ahead and load these right into Excel as well. So there's 3 ways I could do this. I could just take the data, put it into Excel. I could just take the data, put it into the data editor of SPSS, or, which is the easiest, and which is what I did, I can just copy this syntax and just load the syntax into SPSS, and it will provide me with my graph or chart. So that's what I did. And it generates this graph. And so it's an interesting graph. You can see here's our different density values. And here's 3 different temperature values. And so you can see this is low density, high density. Again, the deaths per 100,000, the highest rate of deaths is when we have a combination of low temperatures. This blue dot, see this blue dot is low temperatures. When we have low temperatures and we have high density. When we have low temperatures and low density, our deaths are actually at the lowest. So this is sort of a classic interaction effect. If we draw our lines, which I'm probably bad at drawing, but so that's supposed to be a straight line. If we draw a straight line there and a straight line here and a straight line here, you can see we actually have that X effect. You can see, you know, in the old days of blackboards, this was even worse when I tried to draw lines. So I admit those aren't very straight lines. But anyway, so you can see when temperature is low, these are the 3 temperature is low values, what a huge slope this line has. I mean, this line is a big slope when temperature is low. So if you go back and look at the last slide, you'll see that. When temperature, so if you rewind and look at the last slide, you'll see that this slope is really big when temperature is low. And, you know, in a sense, the worst situation is to have low temperatures and high density. On the other hand, the slope is pretty much flat or even a little negative when temperature is high. When temperature is high, density doesn't make much of a difference. And then for temperature, the average values of temperature, it does go up. So for average values of temperature, it does go up, not as much as when it's low temperature, but there is an increase with density. And that's what we found before. If you remember, if you go back to our previous lecture, you'll see that that's what we found before. So this matches our previous lecture. So the graph makes it a lot easier to see. And now here I've actually put the lines in. So now I let SPSS draw the lines. So I let SPSS draw the lines, and you can see, you can see again this that it forms an X, and you can see what these fitted regression lines here look like. So you can see the same effect. So I let SPSS add lines to the chart, and you can see SPSS draws much straighter than I do. And here again, you can see it. I believe this is our old one. This is the one I drew before with SPSS. You can see this is a little different. With process, this goes down. When I did it before, it goes up. That's because I don't, when I calculated the values for the for plus 1 standard deviation and minus 1 standard deviation, I did a little bit of rounding. So my numbers were a lot more approximate than processes are. So process has pretty exact values for 1 standard deviation above and 1 standard deviation below. Mine were rounded off a little, and so when I plot my chart, this line looks like it's going up a little bit. You can see in the process created charts, this line goes down a little bit. But other than that, it's highly similar. Okay, so if you compare this to the previous chart, you'll see it's very similar. And again, this chart was generated just using SPSS to do the moderated regression analysis. The last chart was generated from SPSS, but the moderated regression analysis had been run in process, and then we cut and paste the syntax into SPSS. Okay, another thing we can do here is to look at a moderated regression where we have a dummy variable or a categorical variable. Now I took a simple dichotomous variable. So we ran this regression before. Here we have, again, deaths, COVID deaths per 100,000, density, and this time region. If you remember, region was coded north-south. So we go ahead and run this. You can see our model summary again, R equals 0.60, which is pretty good for psychology studies, although this really isn't a psychology study. It's more of an infectious disease study. Our R square is 0.37, which would say that 37% of the variance in COVID deaths is explained by this model. Again, at the state level, not at the individual level. Our P is significant, 0.00. When we look at the model, our constant, significant, again, that doesn't matter a whole lot. These are our confidence, our bootstrapped generated confidence intervals for these parameters in the model or for these variables or factors in the model. So for the factor of density, you can see the coefficient here, standard error, T. It is significant. The p-value is 0.01. Region, again, that's north-south, is not significant. The interaction is significant. So again, we do get a significant interaction. Region interacts significantly with density in predicting COVID deaths. And again, region was coded north-south. So it's a categorical or dummy variable. So you can see the product term's key. The interaction is density times region. Okay, again, first we get the test of the highest order unconditional interaction. You can see that that's significant, but that's really just the interaction effect we already had. And this is pretty meaningless when we only have a two-way interaction, because we only have one two-way interaction. That's obviously the highest order unconditional interaction. So this is not going to give us very much information. We have the conditional effects of the focal predictor at values of the moderator. Note in this case, I let it go ahead and center a dummy-coded dichotomous variable, which I'm not sure, that to me doesn't really make sense. I said that before. I just went ahead and did it to see how it would come out. And so you can see when we do it, then it standardizes or centers those values. So we end up with the one region having a -1 standard deviation value of -0.66, and the other one having a +1 standard deviation value of 0.34. And then again, these would be the regression lines at that point, or not, at least the B effects at that point. Okay, so I'm skipping some steps here, but I've plotted the values now so we can interpret them more easily. And you can see, hopefully you can see it, that as the density increases, so do the number of deaths, but only for people who are living in the north. So as density increases, the number of deaths increase, but only for people living in the north. So this would be, these green values would be the north. The blue values are the south. So for people living in the south, as density increases, the number of COVID deaths actually goes down slightly, which is somewhat surprising, I guess. But so we're getting our clear moderator effect again. If I dare to try to draw a line again, which is pretty dangerous, it goes something like this and something like this. And so you can see again, it's a disorderly interaction, really. The two lines cross. Pretty much, again, for the south, it's a flat relationship. There's no relationship between population density and COVID deaths. But for the north, there's a pretty strong positive relationship between density and COVID deaths. All right? And if you go back, this should match up with what we did in our previous class when we did this ourselves using SPSS. If it doesn't, we're all in trouble. And let me know, because then I messed something up as we went along here. All right. At this point, it can really get complex, because at this point, we can start talking about much more involved or complex models. For example, we can have what's called mediated moderation. Let me try to say that again. Mediated moderation. And mediated moderation is when you have a moderating effect, and the moderating effect is then mediated. You can also have moderated mediation, which is when one or more paths in a mediation model are themselves moderated. So not only the models, but also the effects and variables within the models can then be named after their contributions. But this starts to get really complex. So you start to get into really complex models. And again, I'd suggest at this point, you turn to the process book, or Hayes's book, or Hayes's articles, and look at some of the different models that Hayes presents. I mean, Hayes presents an incredible number of already pre-programmed models. So this is just an example of, for example, Model 8. In Model 8, we have a mediation, but then we have two moderators of that mediation. So if you look at Model 8 here, you can see X has a direct effect on Y. X has an indirect effect on Y through M, which is mediation. But then the effect of X on M is moderated by W, and the effect of X on Y is moderated by W. So let me repeat that. This direct effect of X on Y is moderated by W. The indirect effect of X on M is also moderated by W. And note, you could probably also have a situation where W moderates the effect of M on Y. So you can start to get really complex models. And this is model 8. Again, Hayes has a lot of models. I suggest you go to his Appendix A using process, and he'll show you a huge number of already existing models. If what you want to do doesn't fit into that model, you can always customize your model or create your own model. But Hayes does give you a lot of different models. But this just shows you that we can get into this really deep into the woods here, or really deep into the weeds, and we can start all these different models that mix moderation and mediation. I'm coming to you to interrupt this TV show to just make a correction. So just so you have it correct as we go through these slides, I want you to know or remember that despite what I say, death pop is deaths per million. It's not per thousands or 100,000s. It's actually deaths per million. So again, the error, the problem came about because the world site uses deaths per million for each state. On the other hand, most other people use deaths per 100,000, and also for most of the other variables, they used 100,000s or things per 100,000s. So I actually changed in the database the variable or created a new variable that was deaths per 100,000. But then a lot of times I still went back and used the death per million variable by my error. So all it does is put anything off by a factor of 10, really. It doesn't affect the interpretation of any of the analyses, but it does put things off by a factor of 10, and I apologize for that. But instead of changing all the slides, I'm just letting you know that whenever it says death pop, that's deaths per million, not per thousands or 100,000s. And I thank you for your understanding with this issue. All right, so I wanted to do one Model 8 for you. I'm not going to go through and try to do all the interpretations of this, all the various graphs and plots of this, but I did want to at least take you through it, show you it's possible. So again, this would be a Model 8. We have one dependent variable or outcome variable or Y variable. In this case, it's COVID deaths. We have one independent variable or X variable, density. We have one mediator variable, air pollution. And then we have one moderator, region. And again, region, because this is Model 8, region will be moderating the effect of density on air pollution and also the effect of density on COVID deaths. So it'll be moderating those two relationships. And the outcome variable, the final outcome variable again is deaths in the population or COVID deaths. So this is Model 8. If you want to go back, you can, the little model, I just showed you what Model 8 looks like, and you can see what this, how this would then be set up. And again, we've already done analyses using both air pollution and found it to be a mediator, and region and found it to be an interaction. So here we go. Here's what our output would look like. First, of course, we start by predicting air pollution. And if you remember again, then we did say that the relationship between density and air pollution could be moderated by region. And you can see here it's not. I mean, you can see both density and region have an effect on air pollution. They have a main effect. They have a main effect. So density is significantly correlated with air pollution. And region is very highly significantly correlated with air pollution. And so they both have significant B coefficients. Again, these are B coefficients, standard errors, T's, p-values, and bootstrap confidence intervals, except we don't have an interaction. So there's no interaction between region and density in predicting air pollution. So that probably doesn't even really need to be in the model. You know, we could probably throw that out of the model, parsimony, simplify the model. Not that, and I haven't said a lot about this as we went along because I hoped you knew it from the first semester or from, of course, our first 1 or 2 classes. But of course, when I talk in this class, I try to use language that's more understandable rather than strict statistical language. But of course, just because the p-value is not significant doesn't mean that effect could not exist. I mean, again, the fact that a p-value is significant, all it says is that how likely the data is given the null hypothesis. So a p-value just tells us the probability of that data occurring given the null hypothesis. We then have to make our own decisions. Of course, technically, a non-significant p does not mean an effect does not exist. It could just mean we don't have enough power, and probably always some type of effect exists. So, but, even in journal articles and textbooks, if we went through that language every time, it would be hard to ever get anywhere. So we're saying there's no interaction effect. And then again, we only have one interaction effect, and this is the test of the highest order interaction, unconditional interaction. So the interaction effect is not significant. Then the next thing we're going to get is the prediction of the outcome variable, which is deaths in the population, or deaths per 100,000. We can see our model summary, our R is very high, 0.707, our R squared is 0.50, our P, it's significant, 0.000. Then we get our B values. Again, we don't get beta values. Process or Hayes isn't a big proponent of beta values. You can look online to see why that is. But we get our constant. We get our effect for density. You see, density now is actually itself not significant. So the effect of density is not significant. Air pollution is significant. Of course, in this case, we did not have a moderator between air pollution and deaths. Region is not significant. Region now becomes non-significant, but the interaction is significant. So this interaction between density and region is significant. And we really saw that earlier in this class, or earlier in this video or PowerPoint, that there is a pretty substantial interaction between region and density. And so here, region and density is significant. And again, the test of the X by M interaction, that would be the test of density by mediator, and that is not significant. So process will tell us, is there a significant interaction between the X value, which is density, and the M value, which is air pollution. And it's telling us it's not. There's no significant interaction. However, of course, again, there is a significant interaction between density and region. Okay, then it just gives us, for the different values of region, our conditional direct effects of X on Y at our 2 region values. Now you can see this time I changed it up a little. I did not center the dummy variable or the categorical variable. So this time it's just using the 0 and 1 for region. Last time, if you remember, I allowed it to center those values. So last time I allowed it to center those values. And you can see, of course, that there's a large positive effect when for the north. So there's a large positive effect for the north. And then here's our indirect effects. These are indirect effects of density on air pollution, on death, on COVID deaths. And you can see it's going to calculate the indirect effects for each region. And that's because we told it that there was an interaction effect, a moderation effect. So it's going to give us the indirect effects for those 2 different regions. Okay, so what this is it's the indirect effects for the 2 different regions. And then it's going to give us what's called an index of moderated mediation, or a difference between conditional effects. In this conditional indirect effects, in this case, it's actually not significant. So it's telling us that the moderated mediation is not significant. I mean, the reason again we know it's not significant is because these confidence intervals include 0. So the moderated mediation when we go through air pollution was not significant. And, we saw that before. What is significant is the interaction between density and region itself impacting deaths. But the mediated relationship, or that indirect effect, there is not an interaction. And again, we only put the moderator variable on the A path. We could have put the moderator variable on the B path as well, but we only put it on the A path. At this point, I'm not going to get a lot more in depth in terms of trying to interpret or not interpret those effects. You can, of course, plot them. Actually, Process, I didn't show it to you, but Process did give me, again, the syntax, so I could plot the different interactions. In fact, though, and as I told you, I changed the air pollution data. This is the actual air pollution data. If you look at the actual air pollution data right here, you can see that air pollution is not significant. So this is the actual, I put in the actual air pollution data and ran the process model, just in case, you were really interested. And when we put in the actual air pollution data, the effect of air pollution as a mediator is not significant. And then the indirect effects are not significant. So the air pollution itself doesn't really have an effect. There is a moderation or an interaction between region and density. But the effects of air pollution, in all honesty, were not significant. But that wasn't very interesting. So I created some more interesting air pollution data for you. But again, in the real data set that I originally created, where I had the actual air pollution ratings, you can see there's no main effect, or there's no direct effect. This would be the B path. There's no path, that's the path between air pollution and deaths is not significant. So that's why I sort of made up some air pollution data. And at this point, what I just wanted to show you is that you can do other kinds of more complex models. So this was model 8, which is again a model where you have interactions between some moderator, and those interactions can affect any of the paths. In model 8, the interaction is on the C path, or actually you can look at it as a C prime path, but the path between the independent variable, which in this case is density, and the dependent variable, which in this case is deaths. And you can also, which we did have in this model 8, an interaction with the A path, which is the path between density and air pollution. We did not have an interaction with the B path, which would be between air pollution then and deaths. So I hope that makes some sense. Again, these are the types of things that would probably be a lot easier to do in a live class, where I could see if if you understand what's going on, if you could ask questions about what you don't understand, if I could see what I'm saying is just not catching on at all. But I hope you were still able to follow it. Certainly when we get to these mediated, moderated, or moderated, mediated, or even more complicated models, it gets really complex. I mean, again, the best advice I can give you is to start with that Appendix A of Hayes's process book if you want to use process. And again, as I also said, process right now, the official process is not available in R. There are some sort of unofficial knockoffs of process in R, but the official one is not yet available, except Hayes just did put out a beta version, and then I believe the official version should be out in a couple months. So if you want to try out the beta version, you can try it out. I find process runs pretty well in SPSS. Now, another thing, though, again, just like a warning to sort of end this lecture, is that the version field used of process was a little different than mine, quite different, for example. quite different than mine. For example, in that one analysis we discussed, he was able to put a moderator into the mediator slot. Now, I don't know if he could actually do that, if that actually worked. In my version of process for SPSS, a moderator has to go in the moderator slot, regardless of what model you're dealing with. So I don't know if what he did really worked in his version or not. Also, as I said, certainly a lot of the options he gave were different than the options I had. So I don't know if it's because he's using a different version of SPSS, a different version of process, or or a British version, or maybe it's a server version, because I think the server version could be a little different than the PC version. But I just wanted to warn you that you might have to play with it a little bit, because it could be that your version is going to be different than either Field's version or my version. But I will say process is rather easy to run and get the output from in SPSS. It's a nice addition to SPSS that you can run process through it. Okay, well, thanks for listening to me. It's probably a little cold for a Dairy Queen, but this is something from my youth, the old Dairy Queen, what they looked like in the old days. And I just thought I'd end with a happy thought with the Dairy Queen. We only have one more class left, and that's going to deal with logistic regression. So that's really a change in thought patterns to switch to logistic regression after all this process work. Okay, see you for the next class.